Okay, hello here. In this video, we'll be looking at periodic table, where we'll see the definition, periodic law, electronic configuration, classification of periodic table, and periodicity. Okay, I guess we can move on here. That leads us to the next. Periodic table is a table that shows the arrangement of elements according to their atomic numbers. Okay, now that can also lead us to what we call the periodic law. Now, what is the periodic law? The periodic law states that the arrangement of elements in the periodic table is a function of their atomic numbers. Say it again, the arrangement of elements in the periodic table is a function of their what? Atomic number. And let's not forget that a Russian scientist is the one that constructed the periodic table that we follow. His name is Mendeleev. Mendeleev, L-E-E-V. Okay, so we'll come back to this now, but let's look at how to write electronic configuration. This is going to help us in a lot of things we'll be doing. So the first is electronic configuration based on shells. Now, first of all, I want you to know that electrons can be arranged in atoms based on shells. We have the K shell, we have the L shell, we have the M shell, and we have the N shell. First of all, I want to say that the maximum number of electrons that can be in a shell is 2n squared. Okay, if it is K shell, it means that your n is 1. So that's going to be 2 times 1 squared, which is 2. If it is L shell, it means that your n is 2 because L is the second shell. That will be 2 times 2 squared, and that will be equal to 8. If it is the M shell, it's going to be 3. That means 2 times 3 squared. 2 times 3 squared is going to be 18. If it is the N shell, it means 2 times 4 squared, which is going to be 32. Okay, it's important that we know this. So K cannot take more than 2 shell, L cannot take more than 8, M 18, and so on and so forth. Okay, let us continue here. So if I want to write the electronic configuration of elements based on shells, let's see, I can start with hydrogen. Hydrogen here is the first element in the periodic table, so that will be 1, so that's in the K shell. An element like helium is 2, so that will be in the K shell. Next element we have lithium. Lithium is the third element, so only 2 can go to the highest in K shell is 2, so the rest will be L, which is 1. So in that case, if I have an element like sodium, which is the 11th element in the periodic table, the K shell will be 2. The L shell cannot take more than 8, so you have 2 8. 2 plus 8 is 10, so the remaining one will be here, which is 11. The same thing with an element like chlorine. Chlorine is 17, so you're going to have 2. You're going to have 8 here. 2 8 is 10, then 7 in the M shell. So this is how to write electronic configuration based on shells. Okay, so that leads us to the next, which is electronic configuration based on orbitals. Now, the shells are further divided into orbitals. So we have s orbital, we have p orbital, we have d orbital, and we have f orbital. And according to Aufbau principle, there is a way the orbitals arrange themselves. Let me give you a brief meaning of the Aufbau principle. First of all, by definition, Aufbau principle states that when filling electrons into orbitals, that orbitals of lower energy is filled first before orbitals of higher energy. And this is what he did. We have 1s, 2s, 2p, 3s. Let's rub that off. 3s, 4s. Let me stop here. Then here 2p, 3p, 4p. Here you have 3d, 4d. I choose to stop here. I can actually continue further, but according to him, this is the order. You have 1s. After 1s, you have 2s. After 2s, you have 2p, then 3s. After that, you have 3p, then 4s. After that, you have 3d, 4p, then whatever should be here, 5s. So if I should follow the Aufbau principle, this is the arrangement of orbitals according to their energies. I have 1s first. After 1s is 2s. After that is 2p. After that is 3s. After that is 3p. After that is 4s. Then after 4s, you now have 3d. For our level, we are going to stop here. So this is the order. So if I want to write the configuration of hydrogen, let's say hydrogen, this is just 1s1 because only one electron. For helium will be 1s2, okay, because there are only 2 electrons. But for something like lithium will be 1s2, then 2s1, because you should note that s orbital cannot take more than 2 electrons. P orbitals cannot take more than 6 electrons. D orbitals cannot take more than 10. Okay, so please note that S cannot take more than 2, P cannot take more than 6, D cannot take more than 10. So if I want to write the configuration for, let's say, sodium, let's see for sodium. For sodium, Na, sodium is the 11th element, is going to be 1s2, that's 2. After that, 2s2, okay, that's 4. Then you have 2p6, that's 10, okay. So then after 2p should be 3s, so 3s1, making it 11 altogether. That is very beautiful. Now, I want to also say this, that we can use the configuration of noble gases to write the configuration of elements. Like here, 1s2, 2s2, 2p6 is 10 electrons, which is obviously neon. So we can say neon, then 3s1. That's another way we can write the configuration of sodium. Neon has 10 electrons, it's a stable and inert gas. Okay, we have Na, then 3s1. Let's see another example. Let's say we have potassium. Potassium is 19. So that will be 1s2, that's 2. After 1s2, you have 2s2. You have 2p6, that's 10 altogether. Then you have 3s2, making it 12. After 3s should be 3p, 3p6, making it 18, okay? Okay, that means the next should be 4s1, making it 20. Making it 19. So this is the configuration for potassium, but we can still write it as this. From here down here is 18. The noble gas with 18 is argon, so we can just simply say this is argon, Ar, then 4s1. Okay, this is very, very important for us to note. Okay, let's give one more example. Let's write the configuration of sulfur. Sulfur is the 16th element. So this will be 1s2, okay, that's 2. After 1s is 2s, 2s2, making it 4. Then after that we have 2p6, making it 10. Then after that we have 3s2, making it 12. Then after that we have 3p, it should be 3p4 this time around, making it 16. So this is the configuration of sulfur. If I want to write it in terms of noble gases, this 10 is neon, so I can just say neon this way. Then we have 3s2 and 3p4 as the configuration of sulfur. The other way you can write that. Okay, I want to believe that you understand this. So let's move to the next. So here we are going to look at the classification of periodic table. Okay, now the first is classification based on metallic properties. Periodic table can be classified based on their metallic properties. The second is classification based on groups and periods. Okay, you can classify the periodic table based on groups and also based on period. Then the third is classification based on blocks. Okay, so we are going to discuss these three classifications in this video. Now let's move on. Classification based on metallic properties. First of all, now I would like to say this, that group 1 to group 3 elements, group 1 to group 3 elements are metals. Group 1 to group 3 elements are metals. So you see, this is group 1, this is group 2, and this is group 3. They are all metals. Okay, then group 5 to group 8 elements are non-metals. So this is group 5, this is group 6, this is group 7, this is group 8. Okay, they are non-metals. Now if you notice, I have not said anything about group 4 elements. That's because under group 4 elements, okay, you can see carbon. Carbon there is a non-metal. Carbon is a non-metal. You can see, but silicon and germanium. Germanium is Ge. Silicon and germanium are what we call semi-metals. Now these semi-metals are also called semiconductors. Okay, then under the group 4 you also have lead and tin. Lead and tin are metals, okay, in group 4 elements. So group 4 elements consist of carbon, silicon, germanium, lead, tin. But carbon is a non-metal. Silicon and germanium are semi-metals or semiconductors, or what we call metalloids. You can call them metalloids. Metalloids has the spelling METALLOID. Okay, then lead and tin are metals. Okay, now that is it for our level. Now, but in some other climes, as we go higher, boron is also seen as a semiconductor, a semi-metal. But for now, we'll go with this group 1 to group 3 elements. So that means, based on what we've said now, sodium is a metal, Y is a group 1 element, calcium is a metal, is a group 2 element, aluminium is a metal, is a group 3 element, but sulfur is a non-metal, is a group 6 element, argon is a non-metal, is a group 8 element, and so on and so forth. Okay, so we'll move to the next classification. This is based on groups and periods. Now I would like to say this here, that elements in the same groups have the same number of valence electrons. Elements in the same group have the same number of valence electrons, but elements in the same periods have the same number of shells. Elements in the same group have the same number of valence electrons. Elements in the same period have the same number of shells. So I'm going to quickly pick out elements. Look at, for example, look at hydrogen. Hydrogen, the configuration is 1 based on shells. Look at lithium. Lithium is the third element. The configuration is 2, 1. Look at sodium. Sodium is 11th element. The configuration is 2, 8, 1. Look at potassium. Potassium is 19th element. The configuration is 2, 8, 8, 1. Now, have you noticed that all of them in group 1 element, they have a valence electron of 1. Their outermost shell has only 1 valence electron. And that is why they are all in group 1 elements. And this is the same thing that is obtainable in group 2 elements, in group 3 elements, and so on and so forth. So if I have two elements, let's say I am to compare two elements, and I'm asked if they belong to the same group. Let's say I have an element whose configuration or whose atomic number is 16. Let's say an element whose atomic number is 16, and I have another element whose atomic number is 32. And okay, sorry, not 16. This should not be 16. Let's say 8 here, and this is 16. And I'm asked if they are in the same group of the periodic table. What is the relationship between X and Y, element X and Y? What I do is that I write their electronic configuration. For X here, which is 8, the configuration is simply 2, 6. If you remember what we did under configuration based on shells. For y here, which is 16, the configuration is 2, 8, 10, then 6. You see that? So the relationship between x and y is that they are in the same group. Why? Because they have the same number of valence electrons. Look at their valence electron. Okay, that is quite important. Now that leads us to the next. We're saying that elements in the same period have the same number of shells. So let's pick certain elements. Let's look at beryllium, carbon, and nitrogen. The three of them are in the same period. Let's see what is common to them. Now beryllium is the fifth element in the periodic table. The configuration is 2, 3. Carbon is the sixth element. The configuration is 2, 4. Okay, while nitrogen is the seventh element, the configuration is 2, 5. So if you've seen that they have two shells, is 1, 2, 1, 2, 1, 2. They have 2 shells each. Okay, and that is why they are in the same period of the periodic table. Elements in the same period have the same number of shells. Let's look at another example. Look at sodium. Sodium is 11, that's 281. On the same is magnesium. Magnesium is 12, that's 282. Then we have aluminium. Aluminium is 13, that's 283. You see, each of them have how many shells? 3 shells. So because they are in 3, they have 3 shells. That's why they are all in period 3. Okay, they are all in period 3. They have 3 shells, so hence are in period 3. Okay, but boron, carbon, nitrogen have 2 shells, so hence are in period 2. Potassium, calcium have 4 shells, that's they are in period 4. So if I should write, okay, let me try something else here. Now somebody might ask, how do I know the shells when I'm given the electronic configuration based on orbitals? Like I'm giving something like this: 1s2, 2s2, 2p6, 3s2, 3p3, and I'm asked what group and period is this element. What I will do is I'll look for the outermost shell. 1 is the first shell, 2 is the second shell, 3 is the outermost shell. So this is the outermost shell. So outermost shell, there is shell 3. Shell 3 means that this guy is in period 3. Period 3. And in that period 3, how many electrons we have there? 5 electrons. That means it's in group 5. Now somebody else can put it this way. Count the number of electrons. You have 2 here, plus 2, making it 4, plus 6, 10, plus 2, 12, then plus 3 is 15. So 15 means 2, 8, 5. Okay? So valence electron is 5, meaning it's in group 5. Then we have 3 shells, meaning it's in period 3. So those are the 2 ways we can, okay, say that. Now another is we can also have something like this. Let's see another example. Let's say we have 1s2, 2s2, 2p6, 3s2. What group and what period? Okay, the valence electron group 1, period 1, 1 shell, 2 shell. Then this is the third shell. We have only 2 electrons in the outermost shell. So third shell means is in period. Third shell is in period 3. We have only 2 electrons in the third shell, that's group 2. Okay? Or you say 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2, 12. 12 means 2, 8, 2. So 2 here, valence electrons, then 3 shells. Okay? I believe that this is quite clear. Now we'll move on to classification based on blocks. Now look at this is the periodic table that contains all the other elements. The ones we saw previously are for the first 20 elements, but here now we have about 136 elements, if I'm correct. But in this periodic table we can divide it into blocks. Now we have, let's see, we have you see what we have here. We have the S block here, we have the P block here, we have the D block here, and we have the F block here. So I'm going to define them and make it easy for you. First of all, the S block elements. What are S block elements? Now, S block elements are elements whose configuration ends with S orbitals. S block elements are elements whose configuration ends with S orbitals. Now, it becomes easier if we also know that S block elements are actually group 1 and group 2 elements. Group 1 and group 2 elements. For example, sodium is an S block element, because you can be asked which of these this element, they can call an element and ask you what block does this element belong. Sodium is an S block element. I'm going to give you two reasons. Number one, sodium is a group 1 element, so you don't need to bother yourself, because group 1 and group 2 elements are all S block elements. But let's see why it is called an S block element. Now, sodium has 11 electrons. The configuration is 1s2, 2s2, 2p6, and 3s1. Okay, so have you noticed that the configuration ends with S orbital, so making sodium an S block element? But once you know your group 1 element and your group 2 element, you don't need to write the configuration to know that that element is an S block element. Now, for a P block element, what is a P block element? A P block element is an element whose configuration ends with P. Now, but better still, if you look at the periodic table, you can see that P block elements are actually elements from group group 5, group 3 to group 8. Now, the group 3 here, you can call it group 3, or you call it group 13 to group 15, or you say group 3b to group 8b, whichever one is correct. Okay, but just know that any element whose configuration ends with p orbital is an S block element. A good example, sulfur is an S block element. Sulfur is the 16th element in the periodic table. Okay, so the configuration is 1s2, 2s2, that's 4, 2p6, that's 10, 3s2, that's 12, 3p6, no, 12 plus 6 is 18, that's already much, so this will be 3p4. Okay, so you see the configuration here ends with p orbital. Now, but I made it easy for you by saying that an S block element is between group 3 to group 8 elements. Now, that leads us to a D block element. How do I know a D block element? A D block element is an element whose configuration ends with d orbital, or you can say that they are elements that have incomplete or incompletely filled d orbitals. Another name for D block element is called transition element. Transition. Transition. Okay, transition elements. Okay, and you can see there you have scandium, you have titanium, you have vanadium, you have chromium, you have manganese, iron, copper, and so on and so forth. Their configuration ends with D. Okay, I'm supposed to show you how to write their configuration, but we may not go into that now. Let's see for scandium, for example. Sc, scandium is the 21st element. Okay, so the configuration now will be, I can just simply say argon, because argon is 18, so it means after argon, which is 18, I should have 4s2, okay, which is 20. Then after that it should be 3d1, you see that, which is 21. So that's the configuration for scandium. So that's the same way you can write, for the others. Now let's quickly see. Then we have the F block element. F block element are elements whose configuration ends with F, or you say they have incompletely filled F orbitals. Now the F block elements are also called lanthanides and actinides. F block elements are called lanthanides and actinides. Okay, so that is where you have all of those elements as written in the diagram. Okay, so that is classification based on blocks. So we have S block elements, we have P block elements, we have D block elements, we have L block elements, and I've shown you how to know the difference. Okay, so this leads us to another topic, periodicity. Actually, there should be a Y. In the context of chemistry and the periodic table, periodicity refers to the trend or recurring variations in element properties with increasing numbers or increasing atomic number. Periodicity is caused by regular and predictable variation in the element's atomic structure. Okay, so in the periodic table, we can observe certain trends in their properties, both physical and chemical properties, both down the group and across the period. Okay, and that trend is what we call periodicity. So we'll be discussing them here. These are the properties of periodic table we are going to be discussing. We have atomic size, which we can also say atomic radius. We have ionic size and radius. We have ionization energy. We have electron affinity. We have electronegativity. We have melting and boiling point. And we have heat and electrical conductivity. We'll continue this in the next video.